Recording is rolling. Today's Wednesday, August 24th. A couple things I have lined up here. I'm about to have you guys draw some graphs. If you put these graphs in your notes, that's a good thing. I started a story here. I'm going to add to the story. Right? You guys draw some graphs. My other plan for today is to pull out these college physics questions and solve some of these. So to remind you guys, bring you guys in from last couple of days. And some of you guys been absent last couple of days too. A couple of days back, had you guys do this lab, which involved just rolling Hot Wheels cars down those inclines that are still set back there for my other classes. And we tested lots of variables against other variables, controlling for everything else. For example, a classic one is going to be velocity versus time. Definitely know what this graph looks like for lots of different scenarios, including that race car a couple of days back. Now, if we're thinking about just kinematic motion, we're focused on the linear motion portion right now. Things can be moving in a straight line, forwards, backwards, up, down, but we're just going to take one dimension. Right now, we're going to ignore forces and masses for the moment and just focus on really 5 variables. Okay, so tip those again. There's some kind of displacement x, or depending on context, be really careful because here, the top equation AP says final position is equal to initial position x naught plus, and then the rest of the. When I say x, more often I'll refer to that as displacement. So is it displacement or position? Well, you have to look really carefully at the context of the question. Okay, so we've got some kind of location or displacement here. Do like displacement. Okay, how far from position 0? T could represent how much time has passed in seconds. We got 2 v velocities, like speeds, initial and final. Now, those race cars a couple days back were speeding up as they were going down the incline. So they had like a bajillion different speeds from point A to point B. But in these equations, you guys see all you care about is initial and final. All you care about how fast at the beginning, how fast at the end. And if it started from rest, anything that starts from rest, what's your initial velocity? 0 meters per second. Okay. Oh, we also did an example yesterday of a car braking to a stop. Guys, car braking to a stop. What variable do you know just from that statement? Final velocity is 0 meters per second for anything braking to a stop. Okay. And then the last one on here is this A, acceleration. So that's a rate change of velocity. That's like how fast is your speedometer and needle moving. Okay, and these 3 equations will tie all those variables together. I derived the top 2 for you guys, and then I did tell you guys that if you do top 2 system level equations, you can derive the third one. Notice the third one doesn't mention anything about time passing, although I'm sticking in the background. Again, you guys, this page just for practice problems, solve some of these with you guys, and then you guys worked in teams to solve a bunch of. This is pretty much every single linear motion scenario you can possibly get. It's every combination of these things. Because as long as you have 3 of these 5 variables, you can solve with the other 2. There you go. On the other side are some conceptual questions that I do want to eventually do with you guys. If you have a really good core understanding of this subject material, you can do those. And then, of course, gave you guys your actual homework that we're going to eventually pick up. And we're going to design a quiz for you guys that's going to focus largely on the problems from the textbook. Okay, so you guys got that going. And don't forget to a progress check is open. So I need to bump the date because this is actually Labor Day. Oops. Let's change this to Tuesday the 6th. Tuesday 9/6. Okay. No, kinematic motion also includes some projectiles. We haven't quite got the projectiles yet. That's why I bumped this. Give you guys some time there. All right. So you guys ready to put some graphs together? All right. So here's a scenario. You're sitting on a bench, like Forrest Gump. And then 5 meters away, you see this dog sitting by a tree. You guys see this dog sitting by this tree? Right, so he's at the 5-meter position mark, right? Okay. This story is going to be in 3 segments. So I'm about to give you guys a 30-second story. Here's the first 10 seconds. The first 10 seconds, the dog is just sitting by the tree. Okay, let's put together. Do you guys remember those 3 graphs we've been doing for all these different scenarios? Okay, so let's sketch. I think I'll have room for this. Yeah, it's this. Okay. So X versus T, V versus T, A versus T. Just show up the camera. Kind of fits in there. Okay. Well, yeah. Okay. Unfortunately, I chose portrait versus landscape for those papers. I'll have to slide this up and down so you can see it and it shows up on the film. But you guys know those are the 3 graphs we're going to do. Right. So X versus T. So make like this because I'm going to split the story into 3 parts. The V versus T, do this. Make it like a sideways T graph, and this will make sense why. Here in a few moments. And you know, do the same thing for A versus T. Make it like a sideways T because there might be some negative values going on. Okay. So we're gonna always put time in seconds on the horizontal axis for these kinematic motion graphs. Right. Now we've been doing this for a few days, right? Always putting time on this axis. Right. Then we got how far in meters, how fast in meters per second, and acceleration, like rate change of how fast, meters per second squared. Okay. Got those axes set up. Oh, and I did tell you guys too that I'm going to give you guys a 30-second story, and I've written out the first 10 seconds. So let's break this into 3 parts: 10 seconds, 20 seconds, 30 seconds, 10, 20, 30, 10, 20, 30. Okay, so time in second: 10, 20, 30. Okay, right? Okay. You guys good so far? All right, so let's put in the first 10 seconds of the story. Let's graph that. So the dog just sitting by the tree for 10 seconds. Let's look at the motion of the dog. Maybe we should put a title here. So dog motion. Dog motion. Okay. Go ahead. Make those 3 graphs for just the dog sitting by the tree. What do those 3 graphs look like? Walk around class, see how you guys are doing. Oh, since you guys are taking notes, if you're looking at these notes in the future, it might be a good idea to jot down the story too. So I know I have 1 bullet point up there. I'm going to add a couple other bullet points as I add to the story, so that in the future you can look back. Oh yeah, I remember that was the dog sitting by the tree. Okay, so somebody's got the graphs. Yeah, I've missed it. I'm sure somebody's drawn these graphs, right? For the first 10 seconds. Somebody's gonna get this. Okay, I think some of you guys are kind of close. Okay, let me help you guys out. Okay. So the first 10 seconds, the dog's just sitting there, right? At position 5 meters. You guys see at position 5 meters, right? So at time 0, is the dog sitting at the 5 meter position? Like x is equal to 5 meters. Okay. I've embedded the unit in the axis, so this 5 refers to meters. Okay. So there's at least a point there. What about during what about at like the 2-second mark or the 5-second mark or the 9-second mark? Is the dog still at the exact same position? So what does the rest of this graph look like just during the first 10 seconds? Yeah, just a flat line. Yeah, it's just hanging out at the 5-second mark. Okay. How about V versus T? What's the velocity of the dog? Yeah.
He's sitting down.
He's sitting down.
So
it is 0. Yeah, so go here, like right over the axis. Just 0. Make that pretty bold there. Okay. And what's the acceleration of the dog?
0.
Also 0, because the dog's not changing his motion. So there's no rate change of the motion. Okay. Or if you like, properties of graphs. You guys remember yesterday, I told you guys the slope of the x versus t tells you v versus t, slope of v versus t tells you a versus t, right? And since all the slopes are 0, then every graph after this is 0. All right, next point of the story. What's going on from, say, during this next 10 seconds? Let's say the dog sees a squirrel, and the dog runs toward squirrel. Let's say at approximately constant velocity. I'll just say at constant velocity. Constant velocity. Let's say in the positive direction. Say here's squirrel over here. Oh, squirrel tail. Squirrel ears. So in positive direction. During, but maybe I'll express this as an inequality from time is between 10 seconds and 20 seconds. Right, so between 10 and 20 seconds, is there inequality signs? Less than, less than. I didn't give any numbers for that, but what would the graph shape look like? We walk around class and see how many of you get the basic graph shape. And I didn't give you any numbers for that, but regardless of what the numbers are, these graph shapes are gonna look the same. Who's going to get it? Constant velocity. Hey, when you guys were dropping the Hot Wheels cars down the inclines, were those cars going at constant velocity? No, those cars were going at constant what? Or acceleration. Which is going to be different than this, isn't it? We've also been dropping a lot of balls off cliffs. When those balls are falling down the cliffs, are those balls going at constant velocity? No, they're going at constant what? Acceleration. Okay, so I think this set of graphs here is going to be a little bit different than the internet's last couple of days. All right, so here we go. If the dog sees a squirrel and then like bam, just start sprinting towards that squirrel at constant velocity, do you guys think the dog would be picking up location at a constant rate? So look, something like that, like bam. Okay, what's that? What about V versus T? What's that going to look like? Yeah.
Would this be the same, like a line, but above?
Aha, a flat line, but moved up. That's like here. Okay. Oh, ooh, what's this called in math? When you go from here to here, that's called a jump. Yeah, it would be like a discontinuity, right? Like a jump discontinuity. Okay. Now, if you had a motion detector on the dog, do you think it would just like rise very quickly? Okay. Okay. So if you get this exact question on the AP exam, if you draw this, then like as a discontinuity, they should give you the points. There's always a little bit of a like gray area and greater interpretation. Okay? But if you do it like that, or you could do like a very steep change. Okay? I'm going to go and do a very steep change because that's like physically realistic. We do some simplifying in this class. For example, you guys know we've been ignoring air drag for anything falling down the cliff. Okay? But I guess the jump discontinuity could be one of the simplifications. Okay. Ooh, how about acceleration versus time? While the dog is in motion, while the dog's running at constant velocity, what is the acceleration of the dog?
Zero.
Zero. Still zero, isn't it? Still zero. Okay. Now, here's where you might say, well, hold on a minute. The dog wasn't moving enough. Dog is moving. There is some change of velocity. It's a very, very, very abrupt change. Okay. So, suppose the dog was like wearing an accelerometer on his collar, right? Has an accelerometer, right? And it like detects his motion. You guys have an accelerometer on your phones. That's how it knows like which direction your phone is. And so, do you think maybe there's a very brief acceleration at the 10-second mark? Okay, and here's actually what this would look like. Like bam, just very briefly. And just to tie this all together, you guys see how it's a very tall, skinny triangle? Tall, skinny triangle. Hey, does that very tall, skinny triangle have some area? And what does the area under the A versus T curve represent? Change in velocity. All right, so whatever the change of velocity is, meters per second, it's the same thing as the area of that very skinny triangle, meters per second, right? Meters per second squared times seconds is meters per second. Right to that. All right. Then, third point. Now the squirrel runs in the negative direction past the dog and up the tree. And the dog, because we care about the dog's motion, right? And the dog is going to chase the squirrel back to the tree. Okay. The squirrel runs up the tree, and so the dog's going to end up where he started, right? Okay. Oh, and this is this last bullet point. Let's say that's the last 10 seconds of the story. So this is during time is between 20 seconds and 30 seconds. Okay, so that last leg of the story, the last 10 seconds, the dog is chasing the squirrel back towards the tree where he started. What do those graphs look like during that leg of the story? Take a trek around class.
let's say is change in motion as secondary abrupt. But okay, so if you guys are trying to figure out what's going on with acceleration, because this is kind of a weird story in terms of acceleration. Let's say acceleration is just like a fraction of a second. The dog actually changes motion, but this is mostly a constant velocity story. Those acceleration spike from that third graph. Yeah, that's all that's really wrong with that. Okay. So you guys remember yesterday I told you if you're driving in a car or if you're a passenger in a car, what do you feel? Do you feel the location of the car? No, that's silly. Do you feel how fast the car is going? No. See, if you're wearing a blindfold, you can't tell if the car's going 40 or 50 or 60 or 70 miles an hour. You have no idea, right? You might feel it like rumbling around a little bit, it's in motion, but you don't know how fast, right? But you can't feel what in a car? Acceleration. You can feel acceleration, right? So when the dog is at rest and then sees the squirrel and like bolts off, there is a change in motion, but let's say that happens over like a fraction of a second. Okay. So if the dog's wearing an accelerometer on his collar, that accelerometer can like feel that motion. That's why bam, it'll register like a spike in motion. But then when the dog is chasing the squirrel at constant velocity, then here's what constant velocity, right? Velocity is constant. And then there is no acceleration, right? The dog's not accelerating more. It's just going constant velocity towards the squirrel, right? So there's no acceleration. Right? All right. And then, yeah, remember how these graphs are related too. Remember how slope of x versus t tells you v versus t, the coordinates? Look at that. Zero slope, zero coordinate. Here's some slope. Here's some coordinate. Ooh, right? Meters per second, right? And then from here to here, ooh, do you guys see a very, very, very steep line right here? That's a very large coordinate on a versus t. Right? And then to go from a bottom graph up to the top graphs, that has to do with areas and the curves. So the area of this very skinny triangle tells you the change in velocity at the 10-second mark. It's really made from 10 to 10.2 seconds or something, right? It's very, very tiny time interval. And then from the v versus t back to x versus t, do you guys see like a rectangle right here? Let's see, the height of the rectangle is meters per second, the base is in seconds. Guess what is meters per second multiplied by seconds? Meters, right? Meters. Because here, base times height, right? This has some height in meters per second. This has some base and some number of seconds. 10 seconds looks like. What is meters per second multiplied by seconds? Seconds cancels, those are just meters. That means that the area of this here, pretty much rectangle, right? It's pretty close to rectangle, represents the change in location in meters, right? See, from here to here, there's like some location change. Okay. All right. Let's hit this third bullet point. This third bullet point. So the dog runs back towards the squirrel, and at the 30-second mark, let's say, has reached back to the tree. Okay. So what do you guys have for x versus t?
Goes back now.
Yeah, back down the same way. There you go. Boom, just like that. And the dog gets up exactly where you started, right next to the tree at the 5-meter mark. Right? You guys got that? Okay. All right. How about velocity versus time? What do you guys have for that? Negative territory, right? Negative velocity. Because now the dog's running backwards. You guys got it.
Running backwards.
Yeah. Well, he's not physically backwards. That would be a funny dog. But he's running the opposite direction, right? He turns around like and then right? Running tail first dog. Nah. So yeah. About face and then bam, and then back towards the tree, which would be a negative velocity. Now, you might be thinking, well, hold on, if I'm driving around my car only, the speedometer only shows positive numbers because your speedometer doesn't technically read velocity, it reads what? Speed, right? And speed is like the magnitude of velocity. Okay, so it looks like the dog's running like full sprint towards the squirrel and full sprint back towards the tree, right? So do you guys see that the magnitude of velocity doesn't say the speed of the dog is the same in each direction? Right? It's the same magnitude, just opposite direction. Right? And then I guess okay, now here's back to the jump discontinuity. If you're asked this exact question on the AP exam and you show a jump discontinuity, your AP grader should give you full credit. Right? But if you think, well, what is this technically? A little bit closer to actual reality, you have a very sharp change, like a very steep part of the graph right there. Okay. All right, and then the dog looks like comes to rest at the tree. Guys, good. Okay. And last part of this graph.
So while the dog is running back towards the tree, that's negative velocity. What is the acceleration of the dog while he's in mid sprint? Yep.
You can do a good triangle, but it's down.
Ah, okay. Yeah, actually, you're a step ahead of me. Yeah. So you're right though. You're absolutely right. Okay. No. So while the dog's in mid sprint, the acceleration would be 0, but that transition that change, like what's the slope of this very steep line? Isn't that just an extremely negative slope? Right. So exactly. It'd be like bam. I'm trying like that. Hey, which if you compare, I know these are two very skinny triangles. Right? Do these triangles have the same area? No. Which triangle has more area than the other? Guys, oh yeah, you're thinking. I'm thinking here, guys. What property of does the area of the triangle tell you? Change of velocity, right? Because this triangle is some meters per second squared tall. Here, meters per second squared tall, and has a base in some seconds, right? Tick 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 seconds. Okay. Now area of the triangle is 1/2 base height. So it's still these units. So 1 second cancels gets you meters per second. So remember the area under A versus T tells you something about the change in velocity. You guys see that the change in velocity for the dog going from rest to sprint towards the squirrel is like this much. But then when he makes an about face, he goes from like positive that velocity to negative that velocity. That's twice as much, isn't it? Do you guys think that the area of the negative triangle is twice the area of the positive triangle? Right? Because it's twice the change of velocity. Here, let me make up a number. Let's say this is like 8 meters per second. So it goes 0 to 8. Then it goes from, what's the difference between positive 8 and negative 8? 16. Right? Guys see that? Guys go back? Right. Any questions on the dog? Okay. And so most of the story, the vast majority of the stories has to do with like constant velocities. Right? And then also there's a constant position part of the yeah.
If he's running backwards, is it also negative acceleration?
Yeah, it is negative acceleration just at the moment that he turns around. Because while he's turning around, that is a change in motion. Okay. Now, while he's in mid sprint, that's constant velocity. When you have constant velocity, like here's the constant velocity leg, right? Okay. What's the slope of this line? 0 slope, right? Because there's no change in his velocity while he's in mid sprint. That's why it's 0 acceleration during that part. Okay, so you guys ready to move on to next example? Okay. Let's do this. Let's do a set of graphs that everybody should know, but I just want to see if you guys do. Or wait, we refer to my notes here. I had a few scenarios drawn up. Oh, actually, never mind. I do have a new scenario for you guys. So it's gonna go like this. Okay. Do the same as before. I have a picture for you guys. You guys remember your lab a couple days back? Let's get back to your lab, and let's say that there's a race car right. No, sorry. I'm so sorry, guys. Okay, do this. Okay. I'm gonna draw this way just so that the car's rolling left to right. We can go left to right positive direction. It's a little easier to think left to right positive direction because we write the English language left to right. That might help a little bit, right? So let's say the car starts right here, okay? And we're just holding it. We're just holding it right there. Okay. Then what I'm gonna do is I'm gonna give it a flick backwards. Okay. So here, just give you guys a positive direction. I'll call this the positive X direction. So positive is it naturally wants to roll towards the positive direction, right? Okay. Then I'm gonna give it a flick back towards the negative direction. Okay. So flick car in negative direction. Let's say that happens at time 0. So right, you start stopwatch right as you're flicking it back into negative territory. Okay. Let's say it's going to roll up the incline to about here. Let me draw a little ghost car where it reaches its maximum height. Okay. It's going to slow down, come to an instantaneous stop, and then start rolling and start accelerating towards. Well, I guess it's like always accelerating, right? Okay. It's going to start rolling towards the bottom, okay, in the positive direction. So here's the motion of the car. Right? We did it again in case you missed it. Right?
Right, so then car reaches max height, maximum height, and then rolls under influence of gravity. To the bottom of the incline. Okay, and the way I've drawn the picture, that would be in the positive direction. All right, let's do the three graphs for this one. X versus T, V versus T, A versus T. Help you guys out a little bit. You guys know it's going to go into, let's call the original position like 0.0. So this would be at X equals 0 meters. Okay. So make a sideways T graph for your X versus T. Also make a sideways T graph for your V versus T because you might have negative velocities. Okay. And I know. If you guys can figure out what the A versus T looks like also, right? So three graphs. So this could be in meters in seconds. This could be meters per second in seconds. This is going to be meters per second squared in seconds. Okay. Give you guys a minute head start. Check around the room and see who's going to get those three graphs right. So it's like a two-part story, right? Part one, you flick the car in the negative direction, it reaches maximum height. And part two is then it afterwards rolls in the positive direction on down the incline. The car's going to change direction, right? Car changes direction. Help you guys out a bit. Is there any part of that story that the car is ever going constant velocity? No. So this is going to look different from the dog chasing the squirrel, right? So there's no constant velocity part of this graph. I think the car is always accelerating. Yeah. So yeah, where the car starts, we'll call position 0. Okay, go ahead and put that point on the graph anyway. Okay, so time 0 is at position 0, and right at that moment, you flick the car. Okay. Then what? I'll give you guys a dot anyway. At time 0 is position 0, and right at the moment, you flick the car in the negative direction. What does it do? Ah, all right. I do see some of you guys getting it, which is awesome. Okay. You know what I'm gonna do is the same thing I did last few days for some of these stories. I'm gonna actually start with a V versus T and then branch out from there. I want you to do is switch each color. Let's see. Okay. V versus T. And so if you guys click it in the negative direction, as it's leaving your finger, it has a negative velocity. Isn't that true? Okay. So you might have some very abrupt change at the 0 moment, but I'm just gonna start counting like right as it's like leaving your finger flick. So start off with a huge negative velocity like this, right? Negative velocity. Okay. Then, hey, what's its velocity at the maximum height moment? 0, because it's like turning around, right? So it's going slower, up to the max height, and then after that's going to speed up. Right? Hey, slowing down, isn't that like getting closer to 0 velocity? And then speeding up, isn't that like getting further? Okay, so let's say its maximum height moment's like right, boom, like right there. Right at that time. And this look like that. And this would be at max height. Okay. So it would have 0 velocity at max height, right? Hey, the fact that I drew that as like a constant slope line, like a straight line, that means that the motion of the car has constant what? Acceleration. Constant acceleration. So if you guys know V versus T, you can definitely draw A versus T, right? Is that a positive or a negative slope?
positive slope, right? It's positive acceleration. Okay. Is the slope positive regardless of which direction the car is traveling? Here's traveling the negative direction. Here's traveling the positive direction. Here's turning around. Is the slope the same everywhere? Yeah, so is the acceleration going to be the same everywhere? Is gravity always pulling in the same direction regardless of the motion of the car at the same rate? If you only focus on A versus T, would you ever even know when the car turned around? No, you wouldn't even know when it turned around. It's always accelerating the thing. I mean, once it's left your finger flip. Right? All right. Now probably the hardest one. And again, walking around the room, I did see some of you guys got this X versus T graph. Okay. I did give you guys 1 point there. Here, let me mark out the max height. Let me line these graphs up. Max height, max height. They're like lined up at the same time. Okay. All right. What do you guys have for X versus T? What does that look like? Let's see. Does the car start traveling in the negative direction? So it's going to travel in the negative direction. It's going to peak at well, at its maximum height. As far as it'll be in the negative territory. Okay. And then, suppose it takes like 3 seconds to roll to its maximum height. Do you think it'll take another 3 seconds to go back to the original position? In fact, at the original position, do you think it'll be going as fast as you flicked it in negative territory? Right? Here's what I'm saying. You guys think that this speed and this speed are the same speed? Just one's negative, one's positive? Look at that. Right? Hey, look at this part of V versus T. Do you see how this negative triangle, this positive triangle cancel out? That's because going backwards here is going forwards here. And say at the 6 second interval, took 3 seconds to go back, 3 seconds after, right? It's exactly where it started. Right? And it's going as fast as it started. Was that true for one of the graphs we did yesterday was that if you at the edge of a cliff and you throw a ball straight upwards, okay? Do those graphs that we just did now look exactly like that scenario? You throw a ball straight up? Sure does. Remember we were defining down as the positive direction? I think that was yesterday, right? So if you throw a ball straight up in the air, however fast you throw it, it's going up slower, right? And then it's going to come back down. And when it passes you at the edge of the cliff, is going as fast as you threw it, just down instead of up? Yep, sure is. There you go. Oh, and what's the shape of this X versus T? A parabola. Aha, parabola. All right. You guys got that? Good. Any questions so far? Questions so far? Oh yeah. Okay.
The velocity one, the middle one, how are you starting below 0?
Okay, because when you flip the car, right, I'm really just starting the graph when the car is in motion. So if the car's in motion, it has a speed, it has a velocity.
Okay.
Yeah. Okay. Yeah. So now some students might say, well, what if you went like a 1/10 of a second before that, like right before you flicked it? Yeah, you would have to like start at 0 and then like go bam, and that would include your like pushing the car. But typically in this class, you ignore that little part of the story. You just start the car in motion. Yeah.
Why is acceleration like a 0 on the line?
But so
Why is the acceleration like a minimal?
oh, why is acceleration here?
Yeah.
Okay, so the car is always like once the car's in motion, it's always changing its velocity. Right? It's slowing down, moving backward, and then speeding up on down the incline. But it's always under the influence of some component of gravity. Actually, some component of gravity is always pulling it down. Okay. So yeah, it's always tending towards here to put like a little finish line here, a little finish line flag. Okay. It's always tending towards this goal line, like it wants to get here. Okay. So if it's in reverse, it's being pulled towards the goal line. If it's moving forward, it's still being pulled towards the goal line. So the acceleration is always the same direction. Okay. Actually, let me expand on that a little bit. So we're still doing unit 1 kinetic motion. The next unit we're going to do is going to involve forces and masses. Let me give you guys a little flashboard because I'm going to draw something that you guys are going to see a lot in this class. So we'll see some next unit type stuff. Okay. Speaking of this car on this incline, let's look at this car on this incline. Because you guys did a whole lab on this, so you might be wondering, I wonder how much it's accelerating. How much does that have to do with like free fall? Because these graphs do look like some about like throwing a ball at the edge of a cliff, right? It's the same type of graph, but maybe it's like slowed down
right? Because it's kind of hard to detect, like what's the acceleration of this? Or if I sent you with the lab, like just drop the ball and like time it, that'd be really hard to do because it all happens so fast, right? So how much is it accelerating? Could you guys imagine if this incline, if you took this angle to 0 degrees, call it theta for the angle, right? If you took that to 0 degrees, how much would the car accelerate? 0, it wouldn't at all. What if you take this angle all the way up to 90 degrees? Or just make it a wall. You take your toy car, push it against the wall, let it go. Is that going to be pure free fall? That sure would be. Huh. So this angle has something to do with like the fraction of that gravity gets to act. Gravity is 0% here. Gravity is 100% pure free fall here, right? 0 to 100%. Huh. Hey, how many guys think there might be either a sine or a cosine relationship going on between this angle and the proportion of gravity that gets to pull in the car? Okay. Tell you guys something about sine and cosine. You guys remember like the unit circle? You guys remember that sine is defined as, so this is just one perspective. If this clicks make sense, then it'll help you out. If it doesn't, then, well, there's lots of ways to think about these things. I'm just telling you guys one way to think about this. Okay. You guys remember a sine of an angle tells you how far up or down you are? Here's 0 degrees, and then here's 90 degrees, 0 degrees, 90 degrees. Okay. And then cosine tells you how far you are right or left on the circle, cosine of the angle here, right? So for example, sine of 0 degrees is 0 because it's like right on this line. Okay. And then sine of 90 degrees is 1 on the unit circle. So it can go up to like 1, like 100%. Okay. And then cosine is like the other way. So cosine of 0 degrees is 1. And cosine of 90 degrees is 0 because it's right on its axis. Okay. How far you are away from this origin point. Okay. You guys remember that? Okay. Now, if you're watching this this line move, let's say this angle change, right? Call it, here's your theta, right? Like as that angle changes, you guys remember sine and cosine? I told you guys that cosine is a rate change of sine. Okay. So do you guys see during the first few degrees, sine changes very quickly? Okay. And then as this angle gets closer to 9 degrees, like these height changes, it adds a little bit of height, but it adds it very slowly. Okay. So draw a couple of graphs over here. Sorry, these are different graphs. Right. So theta, let me throw in 90 degrees right here, 90 degrees. Okay. Let's do sine of theta and cosine of theta. So I've got 2 different graphs going on, 2 different graphs. All right. So sine starts at 0 and then picks up very quickly and then kind of peters out towards 90 degrees. Okay. And then cosine starts at 1. It changes very slowly at the beginning, right? At these first few, right? The x value changes very slowly, right? And then it changes very quickly as it gets closer to 90 degrees. So that's like, and then it's 0 at 90 degrees. So it's like this, right? So it's a piece of the curve, and then it just oscillates from there. It goes like here, just goes on from there, right? Right. So actually, you know, they may or may not help you with the. But if this doesn't make sense, then that's right. There's different ways to think about this. But what I'm trying to get at is like cosine is the rate change of sine. Okay, let's go back to this. I wonder what proportion of gravity is depending on this angle. Well, if the angle was 0 degrees, you get 0% of gravity. That sure does sound a lot like a sine curve, right? At 0 degree angle, you get 0 of gravity. And if you get 90 degrees, you get 100% of gravity. That's like this point. Hey, how many guys think that there's a sine relationship specifically going on with this angle and the proportion of gravity that pulls? Okay. And I'll prove to you guys with a diagram that do I want to show this to you guys? Yeah, here. This is future content. So if this makes sense, awesome. If not, then we'll just be future stuff. Okay. So in the future, what we're going to do when we're looking at this incline is we're going to split this incline into components. We're going to say, well, the car is constrained along, like moving along the surface. So do you guys see how I introduced a Cartesian system that runs parallel and perpendicular to that surface? We're going to do everything in terms of that new Cartesian system, that rotated system. Okay. And I would say, well, hang on a minute. I know that gravity's pulling straight down. So here's like the weight of, here's the weight of the car. This is going to be like what's called a free body diagram. I'm going to label the forces on the car. Okay. So its weight is pulling straight down. Okay. Hey, is there some support force from the surface, like pushing back? And if this was a completely level surface, would that pushback force be equal to the weight of the car? It would be on a perfectly level surface, but this surface is not level. So it's going to be a little bit less. I mean, I think that pushback force is called the normal force. always pushes perpendicular to the surface. Right? Go ahead and label this weight. This one I'm drawing right now is called the normal force. Normal force. Normal means perpendicular, because it's perpendicular to the surface. Okay? And if I take this weight and I split it into components that are aligned with that new Cartesian system, notice I dashed it. I dashed the components. Does that look like a right triangle? You guys know we just did all that stuff on trigonometry, SOHCAHTOA, right? It's going to come back, comes back all over the place. You guys see how that component is equal to the normal force? Okay, so if the car is on a perfectly level surface, that would just be equal to the weight, right? If you push the car against the wall and let it go, as soon as you let the car go, is there force from the wall on the car? No, because this component would go to zero, therefore the normal force would go to zero. So this normal force actually ends up being, here's what it ends up being. It's the weight times cosine of the angle. I have to tell you one more thing. This angle and this angle, do you think those are always going to be the same angle? Yeah, they think about, like, if you rotate this, same angle. If that's 31 degrees, that's 31 degrees. Right? And then, do you guys see this little short component right here? Well, if this side ends up being weight times cosine of the angle, you guys do see that would be true, right? I have a right triangle here. There's a 90-degree angle right here, right? Here's the weight, hypotenuse, times cosine of this angle. That is that, which is also that. What do you guys think this is right here? What times what? Weight times sine theta, because sine theta is opposite, isn't it? It's going to be weight times sine theta. Okay? Is it to flip to the opposite side? Right? You don't have to know that for kinematic motion, but in unit 2, eventually you're going to have to know. In fact, that's one of the posters hanging from my ceiling. You guys see it right there? Is that poster? Right? Split that into components. And weight times sine theta is the component well, that's the component of the force that actually pulls the car along, right? So if your theta is 0 degrees, sine is 0, 0, then there is no force at all. The car will just sit on a level surface. If you park the car on a wall and let it go, sine of 90 degrees is 100%. So 100% of its weight be like in pure free fall. So the fact that you guys had a 5-degree angle, let's see what your guys' ideal acceleration would have been, like ignoring friction, right? If it's been a truly frictionless system. You guys know Earth gravity is about 10 meters per second squared. You say 9.8 or 10 meters per second squared we've been using the last few days. Okay. What's times sine of 5 degrees? Because you guys had a 5-degree angle, right? And remember, we've been looking at your graphs and I've been telling you guys, like the slope of v versus t should be the acceleration. Okay. Let's see what the ideal acceleration would have been. It should have been 0.87 meters per second squared. Okay. If there was no friction at all. A little friction will slow down from there. Okay. You guys go there? All right. So yeah, all stuff connects. Right? Let's look at some of these problems. Now, I know some of these I assigned to you guys, and some of these I want to do just in class. Okay. In the future, I put this out a little bit better. Like I did write in the future chapter. This is chapter 2 from your book. Chapter 2. Okay. And also your textbook has different sections of questions. Here's some warm-up questions, and there's like the main problem. So in future papers, I labeled that a little bit better on papers too. But you can see how it goes 1 through 9, or sorry, 1 through 13, and then the numbers start over at number 2. Okay. So let me get these warm-up problems. It's pretty good. If the velocity of a particle is non-zero, if the velocity is non-zero, zooming in, right? If you're watching this video, just need to screenshot that real fast. We're gonna start doing these warm-up problems right here. Okay. If the velocity of a particle is non-zero, can the particle's acceleration be 0? And what scenario could that possibly refer to? Constant velocity. Yeah. Hey, we did that today with the dog chasing the squirrel. If the dog was sprinting at constant velocity, there was 0 acceleration while the dog was in full sprint. Right? He was moving really fast, but he wasn't changing how he was moving. Right? You have 0 acceleration and non-zero velocity. Question 2. There's one of these warm-up questions. If the velocity of a particle is 0, can the particle's acceleration be non-zero? Yes. And what scenario would that be? Changing direction. Right? Here, we just did that for this example. Here's 0 velocity and non-zero acceleration. That's like turning around.
But normally you can use that to figure out like the maximum height of a ball. You throw a ball straight up. In this case, the maximum position of the car, like how far did it roll backwards. Right? That's how you can pin locate. Okay. So zero velocity, but non-zero acceleration. That's like turning around. Right? Question 3. If a car is traveling eastward, can its acceleration be westward? What do you guys think? Yeah, and what does that refer to? Yeah, braking, slowing down. Gave you guys a table yesterday. See if I try to dig out all the notes. Here we go. You guys remember this? If you have forward velocity, negative acceleration, exactly. Yeah, that's slowing down. But still moving forward. Because the direction of your velocity tells you which way you're actually moving. Okay. And if the signs between velocity and acceleration disagree, like positive, negative, you're always slowing down. Which is actually both these quadrants slowing down. Right. Question 4. Can the equations in table 2.4, I think they're talking about these 3 equations here. You guys remember these 3 kinematic equations? Right. You guys applied these the last half-hour class yesterday. Right. Solving book problems. Can they be used in situations where the acceleration varies with time? Ooh, I forget if I've talked about this or not. The acceleration here, acceleration. Have we been assuming constant acceleration if there is acceleration? Yes. What if the acceleration is changing at its own rate? Do these equations apply anymore? No. So we'll always deal with constant acceleration scenarios. There might be a weird counterexample here and there. Does anybody know? Here, this is kind of trivia. You don't really care about this for this class. The rate change of acceleration. Because rate change of position of displacement is velocity, rate change of velocity is acceleration. What is the rate change of acceleration called? Does anybody know? Yeah, okay, you do know. It's called jerk. Yeah, it's called jerk. We don't really deal with that class, but some kind of meters per second cubed. Can those acceleration be can those equations be used when acceleration is 0? If acceleration is 0, do these equations still apply? Yes, they do. The top one boils down to distance equals speed times time, or displacement equals velocity times time, I should say. Right. The second one, this goes to 0. The velocity is just the same as it ever is if there's no acceleration. Velocity doesn't change. And the third one's the same thing. Okay. All right, but we got about 30 seconds to the bell, so okay, that's a pretty good pause point right there. Yeah, we will continue on linear motion adventure tomorrow.